Okay, so we have seen how a function which is periodic with period 2 pi can be written as a Fourier series. So far we have restricted our attention to functions with period 2 pi, but there is nothing sacrosanct about this period 2 pi, right? Any function which is periodic with an arbitrary period can be expanded as a Fourier series, right? So we will look at how this, the series expansion can be generalized to an arbitrary period in this lecture. Okay, so sine x and cosine x, sine 2x, cosine 2x, so on is not going to be appropriate, right? If you have some function with some other period, right? Because clearly sines and cosines, as they are, have period 2 pi, right? So suppose you want to, take sine x, and what can you do to tweak this to get a different period, right? So the simple answer is to just include some factor like alpha, right? So instead of sine of x, you consider sine of alpha times x, and now you see that the period of this function will become 2 pi by alpha, right? So if we want this period to be 2l instead of 2 pi, suppose we want the period to be 2l, then you have to fix alpha in such a way that 2 pi by alpha is equal to 2l. So if 2 pi by alpha is equal to 2l, then alpha is equal to pi by l, right? So if you choose alpha is equal to pi by l, then sines and cosines with this factor included are going to be have the right period of interest, right? So therefore the functions sine x and cosine nx will now be generalized to sine of n pi x by l and cosine of n pi x by l, right? If we make this adjustment, all our results concerning Fourier series will generalize to an arbitrary period with period 2l, right? So now we have the expansion f of x is equal to half a naught plus a1 cosine of pi x by l plus a2 cosine of 2 pi x by l plus a3 cosine of 3 pi x by l plus so on, and then the sine part will come in, b1 sine pi x by l plus b2 sine 2 pi x by l, so on. Or equivalently, you could have also written this in terms of the exponential series, summation n going from minus infinity to plus infinity cn e to the I n pi x by l, right? So if you make this adjustment, then of course the coefficients also are going to be given by slightly different formulae. Now the integrals will run from minus l to plus l, right? After all, you have information in an entire period now, and the period is of length 2l. So and this factor outside also changes. You have 1 over l integral minus l to plus l f of x cosine of n pi x by l dx, right? So you can quickly see that in place of l, if you just put l equal to pi, then you will recover all the equations that we have already seen. And bn is 1 over l integral minus l to plus l f of x sine of n pi x by l dx, and cn likewise, right? So you can quickly check that indeed these expressions are all consistent. You can directly work this out from first principles if you wish and extract these coefficients for arbitrary period 2l. Let's look at an example. So the same example, but now with the interval going from 0 to l and l to 2l, f of x equal to 0 and f of x equal to 1 in these two intervals. If we plug in, then we will see that again we'll get either you can think of it in terms of complex exponentials, the series, or you can think of it in terms of sines, right? Both are completely equivalent. Okay, so this is just a short lecture to show you that in fact we have an alternate small tweak, and then we have a general expression for an arbitrary period. Thank you.